Welcome to example number 6 and our discussion of escape speed. So if you were to fire a projectile straight upwards from the Earth, usually it would stop momentarily, and then return back to the Earth. However, if you were to fire a projectile at a certain minimum initial speed, that will cause it to move away, upward, and away from the Earth, and theoretically coming to rest at infinity, this minimum initial speed would be called the escape speed. So this is path 6 that we're looking for. We already talked about earlier in chapter 5 how a velocity that would orbit around the Earth is called the orbital velocity. That would be path 4. And then we discussed just previous to escape speed about elliptical orbits along path, for example, 3 or 5. So now we're looking at the escape speed. So we're going to consider some projectile that is moving away from some planet M. So big M here represents the mass of the planet, and the small little m represents the mass of the projectile that is trying to escape the Earth, for example. We couldn't solve this problem earlier back in chapter 5 because at that point we only knew about forces. And the problem with this particular situation is as the projectile, moves away from the Earth, we know that the force of gravity pulling it towards the Earth is dependent on 1 over r squared. So as r gets larger, the force of gravity gets smaller, and then the acceleration will also get smaller. And so you can't really solve this problem using a sum of F equals ma because the force is variable and hence the acceleration is variable. So really the only way to solve this is using conservation of mechanical energy, which is shown here. So when the projectile is leaving the Earth, initially it has a kinetic energy and it has a gravitational potential energy. And when the projectile finally gets away from the Earth, it has essentially reached a distance of infinity. At that particular point, the projectile stops, and thus it has no kinetic energy. So the velocity final is 0, so there's no kinetic energy. We also know, so since the potential energy is equal to negative g m all over r, as r approaches infinity, the potential energy will approach 0. Hence this term will also go to 0. So therefore it has no potential energy, no kinetic energy at the final position, so in essence the total energy at infinity is therefore 0. So the total energy at the planet's surface must also be 0. That means the kinetic energy must be equal to the negative potential energy, and they must balance out to give you 0. So if you look down here, we're going to move the potential energy term to the other side. Now it becomes positive. We can cancel out the mass of the projectile, which means that you do not need to know the mass of the projectile. It's irrelevant. And so the escape velocity will turn out to be the following expression, square root 2gm over r. So if we're looking for the escape velocity of, say, the Earth, then this would be the mass of the Earth, and if we're launching it from the surface of the Earth, that would be the radius of the Earth. Okay, let's go ahead and calculate the escape velocity for the Earth in example number 6. So the escape velocity for the Earth would be the root of 2gm all over r. And we need to know two things here. We need to know the mass of the Earth. Of course, we also need to know the gravitational constant. The mass of the Earth is 5.98 times 10 to the power 24. And then the radius of the Earth, which is 6.38 times 10 to the power of 6 meters. And so when you substitute all that in there, you should get roughly 11,200 meters per second. So about 11.2 kilometers per second. I should point out as well that at the launch site on Earth, when we would send, say, rockets into space, like Cape Canaveral, they'll take advantage of Cape's eastward speed and use the Earth's rotational velocity. You know that the Earth is rotating on its axis, so when they fire that rocket, they're going to fire in the direction that it is rotating, and they'll get advantage of a 1,500 kilometer per hour due east due to the Earth's rotation. I should also point out that this concept of escape speed helps explain why there is little hydrogen gas and helium gas on the surface in our atmosphere. That's helium here. And the reason for that is the helium and hydrogen particles are quite light. And you'll find later on that their kinetic energy of those molecules are determined by the temperature of the gas. And these molecules will end up having very high average speeds, and hence hydrogen and helium often have a large enough speed that they can actually escape the Earth's atmosphere. So you often don't find these two particles in the atmosphere of Earth. The other more heavier atoms or gas molecules like nitrogen and oxygen and even water molecules have speeds that are greater than if they did have a greater speed than the escape speed, then they would persist to leave the atmosphere. If you look at the moon, for example, the escape velocity for the moon is around, let's see here, it's about 2.38 kilometers per second, and that would explain why you don't have any atmosphere on the moon. All right, and that's our discussion of escape velocity.